Have you ever thought about the strangest, most mind-bending objects in the entire universe? Black holes are definitely at the top of that list. They feel like something out of science fiction, first predicted by Einstein's theories, but so bizarre he thought they couldn't possibly exist. They completely break the rules of reality as we know it. But where do these cosmic monsters come from? How do they work? And what would actually happen if you were unlucky enough to fall into one? Let's dive in. The story of a black hole begins with the life and death of a star. Stars are basically giant balls of hot gas, mostly hydrogen, pulled together by their own immense gravity. Deep inside a star's core, the pressure is so intense that a process called nuclear fusion is constantly happening. It's a colossal engine that smashes hydrogen atoms together to create helium, releasing an unbelievable amount of energy in the form of light and heat. This outward blast of energy pushes against the inward crush of gravity, creating a perfect, delicate balance that keeps the star stable for billions of years. Our own sun is in this stable phase right now, happily balancing these two powerful forces. But for stars much, much bigger than our sun, we're talking giants at least 20 times more massive, the story gets far more dramatic. The incredible heat and pressure in their cores allow them to fuse heavier and heavier elements, going from helium to carbon, then oxygen, all the way up the periodic table until they create iron. This is the star's final act, because for all the elements before it, the fusion process released energy. But creating iron is different. It consumes energy instead of producing it. It's like a fire suddenly running out of fuel and getting colder. With no energy pushing outwards, gravity takes over with unstoppable force. The iron core collapses in on itself in less than a second, imploding at a quarter of the speed of light. This catastrophic collapse triggers a rebound explosion we call a supernova, a blast so bright it can outshine an entire galaxy for a few weeks. In this final, violent moment, the universe is seeded with all the heavy elements, like the gold in our jewelry and the calcium in our bones. What's left behind is either a super dense object called a neutron star, or, if the original star was massive enough, the core collapses completely into an infinitely small point, tearing a hole in the fabric of space-time itself and creating a black hole. So, what are we actually seeing when we look at a picture of a black hole? That perfect black circle isn't the hole itself, it's the boundary known as the event horizon. You can think of it like the edge of a cosmic waterfall. If you're in a boat far away, you can still escape the current. But once you cross the edge, the flow is too strong, and you're going over no matter what you do. The event horizon is that ultimate point of no return. To escape its pull, you would need to travel faster than the speed of light, which, according to the laws of physics, is absolutely impossible. That's why it appears perfectly black. Not even light, the fastest thing in the universe, can escape its grasp. But if that's just the edge, what's at the very center? That's the true mystery, the singularity. Here, our understanding of physics completely breaks down. All the mass of that giant star is crushed into a single point with zero volume and infinite density. It's a place where space and time become so warped that our two best theories for explaining the universe, general relativity and quantum mechanics, give us contradictory answers. It's the ultimate error in the cosmic code. There's a big misconception that black holes are like cosmic vacuum cleaners, aggressively sucking everything up. They aren't. Their power is just gravity, the same force that keeps your feet on the ground, just taken to an unbelievable extreme. If we magically replaced our sun with a black hole of the exact same mass, Earth and the other planets would continue to orbit it just like they do now. We wouldn't get sucked in, we'd just freeze to death without the sun's light and warmth. The true danger is crossing the event horizon. So, what would happen if you did? Time itself would behave in the most bizarre way. To someone watching you from a safe distance, you would appear to slow down as you fell closer. Your image would become stretched and distorted. The light from you would be so stretched by gravity that you'd shift to red, a phenomenon called gravitational redshift, before seeming to freeze in place and fade away completely. But from your perspective, you wouldn't feel anything strange as you crossed the event horizon. In fact, you'd be able to see the rest of the universe in fast forward, like getting a glimpse into the distant future. Once you're past that point of no return, we think one of two terrifying things would happen. The first and most likely fate is a process nicknamed spaghettification. Inside the event horizon, the curvature of space-time is so extreme that there is only one possible direction to travel: down towards the singularity. The gravitational pull would increase so rapidly that the force on your feet would be millions of times stronger than the force on your head. This immense difference in pull, known as a tidal force, would stretch your body like spaghetti, pulling you apart atom by atom until you became a superheated stream of plasma just one atom wide. The second possibility is even stranger. Some theories suggest you would instantly slam into a firewall of high-energy particles right at the event horizon and be vaporized in an instant. The amount of time you'd have would depend entirely on the black hole size. A small, stellar mass black hole would spaghettify you before you even reach the event horizon. But you could probably travel inside a supermassive black hole for quite a while, because the change in gravity over distance is much more gradual. Black holes come in different sizes. The small ones are called stellar mass black holes, which might be a few times more massive than our sun but packed into a space the size of a city. Then you have the terrifying giants, supermassive black holes, which lurk at the center of nearly every major galaxy, including our own Milky Way's Sagittarius A star. These behemoths are millions or even billions of times the mass of our sun and grew by swallowing gas, dust, and entire stars over cosmic history. The largest one we've ever found is S50014+81, a monster that's 40 billion times the mass of our sun. But as powerful as they are, black holes don't live forever. Stephen Hawking discovered that they slowly evaporate over unimaginable timescales through a process called Hawking radiation. It turns out that even empty space is a bubbling foam of virtual particles that pop into existence and then annihilate each other almost instantly. When this happens right at the edge of a black hole's event horizon, one particle might fall in while the other escapes into space, becoming a real particle. That escaping particle carries away a tiny bit of the black hole's energy, which, thanks to $=mc²2, means the black hole loses a tiny bit of mass. This process is incredibly slow, but over eons the black hole will shrink. In its final second of life, it will radiate away all its remaining energy in an explosion as powerful as billions of nuclear bombs. But don't wait up for it. The biggest black holes could take a googol years, that's a 1 with 100 zeros after it, to disappear. By the time the last black hole evaporates, the universe will have long become a cold, dark, and empty place, with nothing left to witness its final, lonely goodbye.